How do you overestimate the dust?
How do you overestimate?
Like at low, like the fact that it's above the 1-to-1 line at low attenuations?
Well, in general, dust looks, when you filter it through broadband photometry, dust looks a lot like old stars, it looks a lot like high stellar metallicities. So you have to disentangle the effects of dust from all these other confusing things going on. Yeah, and that is one way in which you can overestimate the dust. Yeah.
On the simulation recovery, how does that depend on the star formation history? In particular, I'm thinking about the role of the evolved stars.
That's an excellent question. It's addressed a little bit in the next slide, and it's addressed much better at the end of the talk.
Okay.
So, yeah, good question. Energy balance does start to break down, though. And so it breaks down, for example, when you have a very complex mixture of stars and dust. So in emerging galaxies and very luminous infrared galaxies, where the dust attenuation varies significantly throughout the galaxy, throughout different lines of sight, and the emission is non-isotropic. So in this same set of simulations, if you run through a galaxy merger, and you look at how well this assumption does as a function of time, there are certain parts in the merger where the assumption of energy balance, it just breaks down. Things don't work very well. And we start getting very bad answers for dust, which means we're getting bad answers for most of the rest of the SED as well. And so you can see similar things in the observations here. This is a completely unpublished fit I did at some point where there's a local galaxy, R220, which is famous for being alert. It's sort of a big mess of extremely high dust column densities, a lot of infrared luminosity. And you can take the SED, and so here I'm even fitting into the mid-infrared, and then I assume energy balance and try to predict the far infrared, and I fail by about a factor of 4. Okay, so for these very complex galaxies, energy balance just doesn't work that well, and you really need to go out and measure this part of the SED in order to get the right answer. There are ways to make this work a little bit better, and you can do that by building more complex dust models. I talked earlier about how we assume a simple dust screen. This is always a poor approximation of what's happening because galaxies are messy sort of train wrecks of stars and dust. But you can make this approximation better by allowing the shape of the attenuation curve to vary at the same time. And so simulations suggest that as there is more dust in the galaxy, as you get this greater depth that you're looking through towards most stars, you get a flatter attenuation curve. So it's more gray. It attenuates all light more equally. And so you can see that relationship here in this set of simulations by Deshika. And then you can see that this is also observed observationally. If you let the shape of the attenuation curve vary, and you measure it in the observations, you get a similar sort of trend, but somewhat offset. So this is from Salim and Salmon. This is the same thing from my code. So this is something that we do recover, and this sort of helps. It starts to let us model more complex dust distributions while still using this very simple dust screen model.
What is the y-axis again here?
So the y-axis is a shape of the attenuation curve. And so in this case, both these models are assuming a Calzetti attenuation curve, which is a complicated sort of polynomial, and then they add a power law modification on top of that. And so the y-axis is that power law modification. Okay. So this is sort of a band-aid, and it works a lot of the time. It works pretty well. But it will never work if the IR emission is simply not associated with the UV emission. And this seems to be the case in at least a subset of high redshift galaxies. And so here this is an image from Gabriella, who gave a talk earlier this year. Green is molecular gas, red is the dust continuum, and blue is the stellar continuum. And here we have most of the dust and gas emission way over here. We have most of the stellar emission way over here. What we're trying to do is build a model where all the stellar emission passes through all of this dust. And that's a stupid model in this case, because it doesn't. And so these sort of spatially complex and distinct arrangements seem to occur more often at high redshift. And in this case, energy balance won't just work poorly, it will completely break down. So this is one of the cases, again, where energy balance starts to break.
Okay, so I know this is supposed to be a debate. I actually agree with Joel's perspective, but I'm just going to give a slightly different slant on it based on my experience. And I'm going to start. So I'm going to talk about energy balance also, but I'm going to base it on some work that an REU student that did a couple years ago that Howard and I advised. This is Jeremy Dietrich. I assure you he does not usually wear a tie. If you know Jeremy, you know that well. These are a couple random merging galaxies modeled with Segal, panchromatic data sets that Jeremy assembled with quite a bit of labor from GALX and UV out to Herschel in the far IR. And the idea with this much larger data set than is represented here was to figure out how much is the AGN for how much are the AGNs in these merging systems contributing to the overall energy budget. So part of that is disentangling the star formation from the AGN. We happen to choose Segal, the Segal code to do that. The energy balance is between the UV absorption that happens here in this regime and that is re-radiated here. And for those of you who haven't seen a zillion of these plots, what the emission from the AGN is modeled as this green dashed line here, which is very prominent in the mid-IR. The total emission is the black line overall, which approximates the data. And the star formation part, which dominates in the far IR, is this red track. So it's kind of complex here in the mid-IR part. I'm going to talk more about that in a moment. But so the energy, just to recap, the energy balance assumption that everybody uses because it's so useful is that everything that's absorbed in the UV is re-emitted in the far IR, and that's how you understand what the star formation is. Okay, but that assumption breaks down in the ways that Joel already described, and in some other ways. It can break down on short time scales, Chris Hayward and some of the rest of us looked at this a while ago. This was mostly Chris, where he took some simulated disk galaxy mergers that Patrick Johnson, who was here at the time, had originated. So they're indicated here as different masses. So they're equal mass mergers, M00, M1, M1. And these basically bracket the knee of the mass function in factors of 5. Okay, because these are hydrodynamical simulations that track the star formation, and they include the gas and they include the dust, and they've got a prescription for converting the gas to the star formation, and then doing the radiative transfer to track how much emission you get in all the bands that correspond to the observatories we use all the time. You can look at these, you can take snapshots in time of the mergers as they progress and infer how much star formation there is from the simulated far IR emission. So that's what Chris did for these different simulations. And most of the time, the instantaneous, which is what you a priori know from the simulation, the instantaneous star formation rate is reflected well by what you infer from the vertical axis, and that's if you. Sorry, let me just back up a moment. These tracks are 10 megayear steps in time. Okay, so for most of the gigayear long simulations, they inhabit this line of unity. But there's a point where the coalescence occurs when star formation increases by orders of magnitude. A lot of dust is generated. The star formation becomes deeply, deeply obscured and then quenched. And thereafter, the inferred the inferred star formation rate greatly exceeds what we know to be the star formation rate. And this is expressed here in terms of time, okay? So that's one thing. The explanation is that all the star formation gets turned off, but you still have so much hot dust that the young stars are still warm. So you still see that infrared signal, but it's no longer a true signal of the star formation rate that's ongoing anymore. So you might think that's kind of quibbling, but there's a more perhaps serious issue, which is that of small spatial scales. Usually when we do these SED models, we're looking at global SEDs, so we're looking at the integrated light from galaxies as a whole. And I put up this plot from Elbaz et al. 2011, because I remember when this came out, I was really struck by it, because it had so much, it seemed to me to express so much ability to interpret what was going on scientifically. So this is the star formation rate inferred from the panchromatic SEDs of galaxies in the goods fields observed by Herschel, and by and large they track along this line of slope unity as a function of stellar mass. Okay. Although there are some there's a continuum of them that kind of float up above that have much more compact, dense ISMs that are forming stars much more rapidly, and these are the starburst galaxies. Okay, so there's a